Welcome to this explainer, brought to you by Forage College. Look, we are crossing a massive bridge in your Web3 journey today. In our last lesson, you put in some seriously hard work porting Ethereum token standards over to Solana, and specifically implementing those really complex ERC-3643 behaviors. Things like minting authority and account gating primitives. Honestly, give yourself a pat on the back for that. But now, we've got to pivot. It's time to talk about your Capstone project. More specifically, how we take all that brilliant, kind of messy prototype code you just wrote and turn it into something a reviewer can actually, review. We're diving into the integration checklist and Capstone Readiness. Here is our flight plan for today. We're going to hit 5 quick phases: the pre-flight routine, separating evidence from polish, a really practical 4-step workflow, grading your gaps, and finally, getting ready for takeoff. Let's jump right in. So here's the ultimate pain point of any Capstone project. Your prototype works perfectly on your machine. The terminal is green, your tokens are minting, the metadata is totally flawless. But can a reviewer actually prove it? We all know the classic "works on my machine" excuse, right? Well, a working Solana prototype is literally useless if your reviewer suffers a mid-air malfunction trying to guess your specific environment variables or your RPC endpoints or your seed keys. In a Capstone submission, you're answering 2 questions at once. What did you implement, and how can someone else verify it quickly and reproducibly? That brings us to Section 1, the pre-flight routine, safety checks for your code. We're going to lean into an aviation metaphor today, because just like flying a plane, deploying token infrastructure requires some pretty rigorous safety checks. Our first absolutely vital tool is the integration checklist. Think of this as your essential pre-flight manual. It's basically a structured catalog of your claims, like proving that an ERC-3643 feature maps to a Solana primitive, paired with the exact artifacts and commands needed to verify those claims. If you don't have this checklist, you're essentially tossing the reviewer the keys to a plane they've never seen and saying, "Hey, good luck, try not to crash." This checklist is the exact thing that keeps them in the air. And right alongside that checklist, we have the gap log. If the checklist is the manual, the gap log is your maintenance record. When you're going through your checks, you're going to find missing bolts or wonky scripts or tests that just don't pass anymore. It happens. The gap log is where you track every single missing piece of evidence, every test failure, and critically, the exact remediation steps required to fix them. It explicitly links unresolved issues to their owners, so nothing slips through the cracks. Moving right along to Section 2, evidence versus polish. Let's talk about categorizing your artifacts. We need to have a slightly tough conversation here about where devs tend to spend their time versus where they actually should be spending it. We really need to strictly categorize your work. On one side, we have essential evidence. This is the minimal code and proof that your mapping actually works. We're talking mapping tables, deploy scripts, transaction logs showing a restricted transfer, proofs of metadata, the absolute essentials. On the flip side, we have desirable polish. Things like extra unit tests, CI setups, beautiful explanatory diagrams. Now look, I see devs all the time prioritizing pretty diagrams over actual proof. It's kind of like painting hot rod flames on the side of an airplane that doesn't even have an engine. A reviewer will treat missing essential evidence as a hard blocker, but they'll usually forgive missing polish if you've documented it. Sitting right in the sweet spot between evidence and polish are your reproducibility supports. These are the crucial bridges that actually make your evidence usable. We're talking about your environment config, your seed keys, testnet endpoints, and super clear README execution steps. Here is a great rule of thumb to keep in your back pocket. Can a reviewer use these supports to confidently reproduce your entire implementation in under 30 minutes? If the answer is no, your pre-flight check just failed. All right, on to Section 3, the 4-step workflow. Let's talk about how to wrangle all those messy prototype scripts and turn them into solid, undeniable proof. Here is a highly mechanical 4-step sequence you can use to turn experimental work into a rock-solid plan. Step 1, catalog. Just compile every single artifact into folders and write a 1-line claim for what it proves. Step 2, verify. Run some quick sanity checks to confirm each script executes like it's supposed to. Step 3, log. When things fail, and trust me, they will fail, capture those in your structured gap log. And finally, Step 4, prioritize. Assign a criticality level and an owner for every single gap. The final output of that workflow is this beautiful, completely objective table. This is exactly what you want sitting inside your integration checklist. Notice how it lays everything out. You've got the claim, why it matters, the specific artifact, the type of evidence, and a super clear pass/fail status. For instance, minting authority verified. It proves controlled issuance, points right to the deploy_mint.sh script, uses a transaction log as evidence, and gets a big ol' pass. When you present your capstone like this, you're making the reviewer's job absolutely trivial. But you know what happens when you inevitably get a fail in that status column? Well, that brings us to Section 4, grading your gaps and evaluating those failure modes. Borrowing from our aviation theme again, failures have different severity levels. We highly recommend using a 3-tier grading system here. Critical gaps, those completely block verification. The plane cannot fly. Period. Major gaps might block automated tests, but a reviewer could still manually go in and verify the behavior. And minor gaps, those are just cosmetic or optional. By grading every failure, you can logically prioritize your remediation work. You gotta fix the critical engine failures before you start worrying about the in-flight entertainment, right? Let's look at a concrete example of a major gap. Imagine your on-chain metadata mapping uses a non-standard JSON field name. It technically works, but it completely breaks standard metadata schema validation. It's not critical because the token still functions, but it's major because clients relying on standard schemas are going to crash. When you log this gap, don't just write something lazy like metadata broken. Actually, scratch that. You need to be incredibly specific. Note the exact schema mismatch and link it to the specific test that fails. Linking the gap to a failing test converts a vague, scary problem into a highly actionable task. Which brings us to the final stretch, Section 5, ready for takeoff. Let's do our final checks. The ultimate goal of this entire consolidation phase is to transform raw data into explicit claims. You aren't just handing your reviewer a zipped folder full of PDA derivation tests and DevNet endpoints. You are providing explicit claims, backed by exact copy-pastable verification commands that they can run in seconds. You are turning vague files into hard, binary pass-fail statements. I want you to remember this core philosophy. Explicit criteria turns subjective judgments into objective checks. I absolutely love that. When you provide an exact command and an expected output snippet, you completely remove the reviewer's subjectivity. They don't have to sit there and guess if your code is good enough. They just run the check. It passes or it fails. And honestly, that is the gold standard for a capstone project. So, what happens after you've built out this flawless checklist and a prioritized gap log? Well, it perfectly shapes your next step: project planning and token mapping strategy. Putting in the discipline now makes the actual execution phase of your capstone completely measurable and reviewable. You're going to know exactly what you need to build, what you need to fix, and what you need to prove. And that's a wrap for today's explainer. I really hope this methodology helps you confidently prepare your ERC-3643 implementation for its final review. Remember, a working prototype is only half the battle. Proving it works is what actually gets you across the finish line. This explainer was brought to you by Forge College. I highly encourage you to head over to forge.college to continue your Web3 journey, dive deeper into Solana development, and explore some really amazing resources. So, I'll leave you with this. If a reviewer pulled your code right this second, would your project soar through the clouds or stall out on the runway? Keep building, keep verifying, and I'll catch you in the next one.